In this video, we continue with Chapter 1, Examples and Concepts, and we take a look at the definition of orthogonal vectors. So two vectors, u and v in Rn, are orthogonal when their dot product is 0. And so we think about that as that the vectors form a right angle. So down here in the center is my 2D picture, and that happens when theta is pi over 2, thinking about the two-dimensional space. And so here are visuals of what the acute angle looks like, what the obtuse angle looks like. So here's your acute angle, here's your obtuse angle. You can also see if the vectors are in the same direction, you're going to have theta equals 0. And if the vectors are in the opposite direction, you're going to have theta equals pi. So let's determine whether these vectors u and v are orthogonal, parallel, or neither. So here's u, 218 in R2, and here's v, 3/2 and -1/6 in R2. And so we're going to do u dot v. So component-wise, we can multiply 2 times 3/2 plus 18 times -1/6, and that works out to be a 0. We get a 3 plus a -3, so we can say these vectors are orthogonal. Since this is R2, you could go ahead and graph them and see that they do in fact meet at a right angle. I don't really have enough space here to try to draw out where that point 218 hits, but go ahead and sketch out a grid and plot these out as the endpoints and extend your vectors from the origin and see they do meet at a right angle there. So now let's look at these vectors. Vector u is -1/3, 2/3, and vector v is 2, -4. So you could check the dot product if you want. We're not going to get 0 there. You can kind of already see that. But if you check component-wise here, you get -1/3 multiplied by 2. So that's going to give us -2/3 plus, then you're going to get 2/3 multiplied by -4. So that's going to give us -2/3 minus 8/3, I think. So that'll be a -10/3, which is not 0. So you can show, okay, definitely not orthogonal here. So then you start to look and see, well, are there any scalars that could multiply by one vector or the other? And so we see here v equals -6u, so the vectors are parallel. If you're not sure if they're parallel or not, you can do some component-wise division. So you could say, 2 divided by -1/3 and -4 divided by 2/3. And then you could see here, oh yeah, this is just going to be a -6 because we get to flip that fraction and multiply. And then this is going to be -12/2. Which is also -6. So you can, by hand do your component-wise division to check for parallel. And so since we get that here, we say these vectors are parallel, they're not orthogonal. Obviously, it's one or the other. Here's a scenario with vectors u equal 0, 1, 0. And vector v is 1, -2, 0. You can see right away it's not parallel. They're not scalar multiples. When you do the dot product, you get -2, which is not 0. So the vectors are also not orthogonal. So because the vectors are not orthogonal, we can say, okay, not orthogonal. Then we can check, okay, also not parallel because they're not scalar multiples of each other. So this is a neither situation. And if you really weren't sure about whether they were parallel or not, you can start dividing, although you're going to run into troubles here with the 0 divided by 0, but you're going to see, okay, if I divide the first component and the second component values, I'm not going to get the same value there. Okay, in our next example, we're going to determine all the vectors that are orthogonal to vector u equals 2, -1, and 1. So vectors are orthogonal if u dot v is 0. So we're going to plug in our values for vector u, and then we're going to keep generic v1, v2, v3, and then we'll go through the dot product calculations. So it's going to be 2v, u2 is a -1, so it's going to be minus v2. u3 is a 1, so that's a plus v3 equals 0. So then you can let v be your free variable. And so we'll let v1 be t, we'll let v2 be s, and then v3 you can write as a linear combination of those, because you'd have 2t minus s plus v3 equals 0. So if you move the 2t minus s, bump it over to the other side, and so that's where our third component here comes from. So you can find all the vectors that are orthogonal to a given vector in terms of the free variables. So you can use t and s or whatever other variables you'd like. Okay, the Cauchy-Schwarz inequality can also be used to prove what's known as the triangle inequality. It's this theorem 5.5 below here. So it says the norm of u plus v is always going to be less than or equal to the norm of u plus the norm of v. This is named triangle inequality comes from what we see here in diagram A, where we can draw these out in R2 as 3 vectors: the norm of v, the norm of u, and then the distance are these norms. So the norm of v is the distance of vector v, the norm of u is the distance of vector u, and then the norm of v plus u is the distance of u plus v, v plus u, u plus v. It doesn't matter what order you say it in. And so when you draw out our diagram here, you see you get these 2 triangles, and the pink dashed lines complete the triangles there. So that's where the name triangle inequality comes from. So you consider that, you know, the norm of u and the norm of v are the lengths of the 2 sides of the triangles, and then the length of the third side is the norm of u plus v. So the length of any side of the triangle cannot be greater than the sum of the lengths of the other 2 sides. So this follows from what we know about triangles. It also can be proven directly from Cauchy-Schwarz. So we have this relationship, norm of u plus v is less than or equal to the norm of u plus the norm of v. And then down here in part B, we've got an attempt at a 3D drawing. It's kind of hard for me to see there, but you can try to imagine that these endpoints are all in 3-dimensional space. All right, so from our proof of the triangle inequality, we get this relationship that if we square everything here, we have u plus v norm squared equals u squared plus the middle term 2u dot v plus the norm of v squared. And I realized I don't think I included the proof of the triangle inequality, so let's head over to a blank screen over here and prove that out. I left that slide out, so I'll handwrite it for you. So we're going to start with the norm of u plus v, and we're going to square it. So that is u plus v dotted with u plus v based on our definitions. And so then I can pull up my u here, and so I can say, well, that's just u multiplied or dotted with u plus v dotted with u plus v. Okay, so I'm just using my properties from theorem 5.3, my properties of the dot product. So that was property 2 in action. And now I can separate this out to say, well, this is just u dotted with u plus 2 u dotted with v plus v dotted with v. So you can see if we separate out the terms, we're going to get 2 of the u's dotted with v's added up. And then I can just say, well, this is just the norm of u squared plus 2 u dot v plus the norm of v squared. I know it's better when I type things out because my handwriting is not perfect with the pen. And then, well, u dot v right here could be positive. It could also go negative because it's component-wise. So this is going to then be less than or equal to the norm of u squared plus 2 times the absolute value of u dot v plus the norm of v squared. Okay, so now we get to bring in Cauchy-Schwarz. So by Cauchy-Schwarz, I'm just going to call it CS. That's commonly used to represent Cauchy-Schwarz. We know that u dot v, absolute value here, is less than or equal to the norm of u multiplied by the norm of v. All right, so now let's plug that into our proof here with the less than or equal to's. So we are going to have, now that the norm of u plus v squared is less than or equal to the norm of u squared plus 2 times the absolute value of the dot product of uv plus the norm of v squared. So that's where we left off. And now by Cauchy-Schwarz, this is less than or equal to the norm of u squared plus 2 times the norm of u multiplied by the norm of v plus the norm of v squared. And so we can pull all this together. Well, this is just right here equal to the norm of u plus the norm of v by, using FOIL backwards here, or factoring for quadratics, squared. All right, and then we know we've got some non-negatives here. So we know that both norm of u plus v up here is non-negative, and we know the norm of u plus the norm of v is non-negative. So we can take the square root of both sides. So by square rooting, we get this relationship, that the norm of u plus v is less than or equal than the norm of u plus the norm of v. So that's our triangle inequality proved. And we sort of saw proof by picture earlier. All right, my pen doesn't like writing this much. All right. Okay, so again, we were allowed to square root because we knew both those quantities I circled in red were going to be non-negative. So that was our proof of the triangle inequality here that I have circled in red back in theorem 5.5. And so from that proof, we had this middle relationship here that I've got in blue. So if u and v are orthogonal, a right angle, well, then that middle term right here, u dot v is going to be a 0, and that's just Pythagorean theorem. When you've got a right angle, like we see over here in the two diagrams at right in 2D and 3D. So this is R2, and this is R3 down here. So when the vectors are orthogonal, we get 0 in the middle, and we get good old Pythagorean theorem. The sum of the vectors squared, or the sum of the length of the vectors, the norm of the vectors squared, equals the norm squared of vector u plus the norm of v squared. So good old a squared plus b squared equals c squared, because we know the norm of u plus v is the hypotenuse there in the triangle. And here's our visuals over here. So you can see here's our hypotenuse in 2D, and here's our hypotenuse in 3D. Okay, so let's verify this Pythagorean theorem. For the vectors, u is 3, 4, -2, and v is 4, -3, 0. So you first have to check that they're orthogonal. So double check your dot product u dot v, and you're going to get 0. Then we can note that the norm of u plus v, if we add them up, u1 plus v1 is 7. u2 plus v2 is going to be a positive 1. And u3 plus v3 is going to give us a -2. So if you do that norm, you get a 54. That makes sense. 49 plus 1 plus 4. And then the norm of u is going to be 29, and the norm of u squared is 29, and the norm of v squared is 25. So if you add all these up, you get 54 equals 29 plus 25. Okay, so in the group work, you are going to practice the Pythagorean theorem and the triangle inequality and Cauchy-Schwarz. And you can do any calculations you want in Simply, but most of your calculations you'll probably find fast enough to do by hand.